Hello, Matthews, Gatos here. In this video, we're going to look at how to prove trig identities. So let's get started. First thing I want to review with you is how to state your non-permissible values. So non-permissible values are based on things you can't do, such as divide by 0. So 1 minus cos squared cannot equal to 0, and sine squared theta cannot equal to 0. So we're going to solve for the non-permissible values in each one of these. So here I will add cos squared to both sides, and then take the square root, remembering when I do, it's always plus or minus. So square root of cos squared is cos, square root of 1 is positive and negative root 1, which means cosine cannot equal to plus or minus 1. Over here, sine squared theta can't equal 0. Square root of both sides, sine can't equal to 0. So let's look at our unit circle to see where cosine is positive and negative 1. There's negative 1. There's positive 1. And when sine can't be 0. So it looks like it's the same point. So it's going to be at 0, pi, 2 pi, etc. So I'm going to write that in general, saying theta cannot equal to multiples of pi, where n is an integer. So that's how you state non-permissible values. You have to state your MPVs for every question unless it says prove true for all permissible values. Okay, let's review how to do verification. So to verify, I'm going to replace all of my x's with 2 pi over 3. And then I'm going to find out the value of each of these ratios and work it out to see if the left side equals to the right side. So 2 pi over 3 is a nice point on the unit circle. So I'll go to my unit circle and look at where 2 pi over 3 is. And I can see 2 pi over 3 right here. So this is the coordinate that I'll be using. So I know that sine is my y coordinate and cosine is my x coordinate. So just substituting that in, all over root 3 over 2. Okay, so let's simplify in this fraction the denominator. 1, take away negative a half. 2 negatives make a positive. 1 plus a half is 1.5, or 3 over 2. On this side, 1 plus negative a half is positive a half, all over root 3 over 2. So now what I'm going to do is simplify by getting rid of my denominator. So I'm going to multiply top and bottom by 2. 2 over 2 is 1, so that's fair. Multiply top and bottom by 2. 2 over 2 is 1, so that's also fair. So here the denominators all cancel. And what I'm left with is root 3 over 3 equals to 1 over root 3. So all I have to do on the right-hand side is rationalize my denominator. I'll multiply top and bottom by root 3. So I have root 3 over 3 here, and then 1 times root 3 over root 3 times root 3 is 3. So I have verified that the left side equals to the right side for 2 pi over 3, but I want you to remember that verification is not equal to proof. So what we've done is we've said it might be an identity. It's true certainly for 2 pi over 3, but we don't know if it's true for all values. So let's get into proving. So this one here, I want to prove true for all permissible values. So since I said that, that means we don't have to state any NPVs. If I didn't say that, you would want to state your restrictions. So first thing I'm going to do is draw a 2-column proof to separate left side from right side, and also to remind myself not to work across the equal sign. So looking at this one here, they're all in terms of sines and cosines. I am going to go to the left side because that's a little bit more complicated, and I'm going to add that using a common denominator. So using a common denominator, I need a factor of 1 minus sine theta for the denominator of my first fraction, and I need a 1 plus sine theta for the denominator of my second fraction. Okay, so to make those equivalent fractions, if I look at my first fraction, I need to multiply top and bottom by 1 plus sine theta. So if I have 1 plus sine theta multiplied by cos theta, I know that if I were to cancel those, I'd end up with what I started with, so I know it's equivalent. So let's do the same thing for the next one. I'm missing a factor of 1 minus sine theta, so I will multiply top and bottom by 1 minus sine theta. And again, if I were to cancel these, I would end up with where I started. So I know that I have not changed the value of the question. Okay, let's distribute it in here. So I'm going to do cos times 1 plus cos times sine plus, in the numerator here, distribute the cos in. Cos times 1 minus cos times sine. And that will all be over the common denominator. Okay, so in the numerator, I have a cosine. Take away a cosine is gone. So I'm left with 2 cos theta. Now that's looking promising because I have a 2 there, but I don't have any sines in my denominator. So what I'm going to do is actually expand my denominator. So I have 1 minus sine times 1 plus sine, so that's 1 times 1. And then I have a sine theta minus a sine theta minus a sine squared theta. Oopsie, there we go. Minus a, there we go, sine squared theta. Let's continue this on here. Sine theta take away sine theta is 0. So I really have 2 cos theta over 1 minus sine squared theta. And hopefully you recognize that as a rearrangement of Pythagorean identity number 1. 1 minus sine squared is actually just cos squared. So cos divided by a cos squared is just 2 over cosine theta. And if we go all the way back up here, that's what we started with, 2 over cosine theta. So this is a proof because now left side equals to right side for all permissible values. So we've proved it true, therefore Bob's your uncle. Let's look at proof number 2. So in this one here, again, I'm going to right away do that 2-column proof just to remind myself, don't work across the equal sign. And looking at that, I see the left-hand side kind of looks like a quadratic. So this is a strategy I showed you guys in class. 3x squared plus 5x minus 2 all over 9x squared minus 1. I think sometimes those are easier to factor than with the cosine. So let's try that and then we'll parallel our factoring. So in the numerator and denominator, I have factorable quadratics. So here 3x, I can get that by doing 3x times x. To get 2, I'm going to do 2 times 1. I want the 3x times 2 is 6x to be positive and that to be negative. And then in the denominator, it's a difference of squares. So square root of my first term, square root of my last term, add 1, subtract the other. And that's how it factors. So I'm going to do the exact same thing beside it with cosines. Now, if this doesn't help you, you can go straight to factoring with the cosines. So I know that this is going to factor as 3 cos theta minus 1 times cos theta plus 2 all over 3 cos theta plus 1 and 3 cos theta minus 1. So I'm replacing each of the x's with the cosines. Okay, so now I can see 3 cos minus 1 cancels with 3 cos minus 1. So I have cos theta plus 2 all over 3 cos theta plus 1, which is the exact same thing that I have on the right-hand side. So I've now shown that left side equals to right side. I've proved it true, therefore Bob's your uncle. Okay, our last proof here. Again, proving true for all permissible values. Let's do a 2-column proof. And I'm going to use that factoring trick on the last one as well to help us out here. So I have sine exponent 4x minus cos exponent 4x. And I want to show that that's equal to 1 minus 2 cos squared. So this is kind of like a exponent 4 minus b exponent 4, where a is sine and b is cosine. If I wanted to factor that, the first thing I would do is factor it as a difference of squares. So square root of the first term, square root of the last term, add 1, and subtract the other. So let's start with that. So to start with that, I'm going to factor it right underneath. So a is sine, so this is sine squared x plus cos squared x. And then that will be multiplied by sine squared x minus cos squared x. Okay, hopefully you recognize that first factor as Pythagorean identity number 1. Sine squared plus cos squared is 1. So this is really 1 times sine squared x minus cos squared x, which is just sine squared x minus cos squared x. Now I want to prove that that's equal to 1 minus 2 cos squared x. So it doesn't look like I'm on the right track yet, but I'm close. I recognize this as a double angle identity. So see how sine squared minus cos squared, really similar to cos squared minus sine squared. And then 1 minus 2 cos squared x is very similar to this one here. They're same but opposite. So look at this one here. Cos squared minus sine squared, and I have sine squared minus cos squared. Same but opposite. So I can write this as negative cos of 2x. So it's the double angle identity for cosine multiplied by negative 1 because everything's switched around. Look at 1 minus 2 cos squared. That's similar to 2 cos squared minus 1. So same but opposite. So I know on this side, this is also the negative of the double angle identity. So I know that I've proved those true for both sides. Another way that I could prove that, if you don't love that way of proving it, is replacing with sine squared or cos squared. So if I look at this, I can, as an alternate proof, okay, so this is proof number 1 to that point, or let's look at an alternate to that. So if I had sine squared x minus cos squared x, I know that sine squared, because cos squared plus sine squared equals 1, I know that sine squared is the same as 1 minus cos squared x. So a rearrangement of Pythagorean identity number 1. And then looking at that, I have 1 minus cos squared is minus 2 cos squared x. And then that is also the same, if I go all the way up here, as 1 minus 2 cos squared x. So I know that it's the same on this side as well. So 2 different ways that you could end that proof. But either way, we see that left side equals right side. We have proved that true, therefore Bob's your uncle. Couple of things that I want to highlight in this here. The main idea, always draw that vertical line down from the equal sign to separate left side from right side, because I never ever want you to work across the equal sign. Always start with the more complicated sign. The side, try to write it in terms of sines and cosines. Have your formula sheet out to help you. Never ever divide both sides of an equation by a variable. And proofs are true for all permissible values, so you don't have to state your restrictions. But do remember to end your proof with left side equals right side, and of course, Bob's your uncle. So I hope this video helped. If it did, give it a thumbs up, and I look forward to seeing you for the next one.